so we're talking about discrete and continuous random variables. Okay, so we talked about previously about the difference between discrete and continuous, right? Discrete meaning you can only have certain values, right? Whereas continuous is you can have a long spectrum. Along the spectrum, you can have all kinds of different values there, right? Okay, so we kind of know that. So let's look at 6.1. It says discrete and continuous random variables. Go to page 362. 362. There's a definition there. It says, a random variable takes numerical values that describe the outcomes of a chance process. Okay? And the probability distribution of a random variable gives its possible values and the corresponding probabilities. Okay, so the example that they use is tossing a coin 3 times and finding the number of heads. So I'm going to toss it 3 times. So if I toss it 3 times, this is what I can get. Okay, what else am I missing here? I am missing T, H, 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 T, H, 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 T, and then I have all heads. 1, 2, 3, 4, 5, 6, 7, 8. I have 8 different cases, right? Because I can have 2 times 2 times 2, right? So it'd be 8. Okay, so here we go. So the chance of this happening is 1/8, 1/8. They're all 1/8, right? Because they're 1/2 times 1/2 times 1/2, right? Number of heads here is 0, 1, 1, 1, 2, 2, 2, 1. This is 3. 3. So the chances that I'm going to roll no heads is 1/8. Times the chance that I'm going to have 1 head is going to be 3/8 because I have to add these 3. Chance of me getting 2 are 3/8. Chance of me getting 3 are 1/8. Okay? So if I rewrite this into a probability distribution, okay, what I'm going to do is that the number of heads would be 0, 1, 2, 3, and the probability of this was 1/8. This was 3/8, 3/8, and 1/8, right? So this is your probability distribution. Okay, nothing fancy. It's a probability distribution. So what needs to happen here? What needs to happen is you have to make sure you have all of the possibilities. And you also have to add these to be 1. These all have to be they all have to add to 1, right? For it to be a probability distribution. Okay? So underneath there is a discrete random variable. A discrete random variable X takes on a fixed set of possible values with gaps between them. Fixed set. So there is a fixed, right? 0, 1, 2, 3. You cannot have 2.25 number of heads, right? You can only have 0, 1, 2, and 3. So this is a discrete random variable here, right? Okay. So there's a little green box underneath on page 362. Go ahead and take a quick gander at that. Should be self-explanatory. Okay. Let's look at the example there, the example of the APGAR score, an APGAR score. Okay, go ahead and read the problem. Somebody, let's have Alia read it, as long as her dog's not barking.
No, dog's not here anymore. Okay. In 1952, Dr. Virginia APGAR suggested 5 criteria for measuring a baby's health at birth. skin color, heart rate, muscle tone, breathing, and response when stimulated. She developed a 1-2 scale to rate a newborn on each of the 5 criteria. A baby's APGAR score is the sum of the ratings on each of the 5 scales, which gives a whole number value from 0 to 10. APGAR scores are still used today to evaluate the health of newborns. Although this procedure was later named for Dr. APGAR, the acronym APGAR also represents the 5 scales: appearance, pulse, grimace, activity, and respiration. What APGAR scores are typical? To find out, researchers recorded the APGAR scores of over 2 million newborn babies in a single year. Imagine selecting a newborn baby at random. That's our chance process. Define the random variable x equals APGAR score of randomly selected newborn baby. The table gives the probability distribution of x.
All right, thank you. So this is what the APGAR score is. The APGAR score is a cumulative, you're adding these things together to get a score, okay? And the 5 things were appearance, pulse, grimace, activity, and respiration. You get 0 to 2. So if you get 10, that means you score very well in appearance, pulse, grimace, activity, and respiration. Basically, that means you are a very, very healthy baby. Okay? So that's what this is. And if you look at there's a probability, and every score is rated a probability except for 0. Okay? So how would you find what 0 is? You would just add the rest and subtract it from 1, right? Because you have to add the probability distribution, all the probabilities when you add them together have to add to 1, right? So if you look at the solution, that's exactly what they did. They added all the other ones and subtracted it from 1 to find that the 0 was 0.001. So 1 in 1,000 times, all right, you will have a baby that scores a 0 on the APGAR score scale. I would hesitate to, I don't know if I want to see what a 0 baby looks like. Anyway, so B, doctors decided that the APGAR scores of 7 or higher indicate a healthy newborn baby. What is the probability that a randomly selected newborn baby is healthy? So you would go from 7, 8, 9, and 10, and you would add those 4 probabilities together. You would add 0.099 plus 0.319 plus 0.437 plus 0.053. And if you add those together, you get 0.908. What does that mean? That means that 90.8% of the time, according to the APGAR scale, you will find that the baby is healthy. Okay? All right. Let's go move on. Flip the page. There's a little red dot there. Be sure to consider whether to include the boundary value in your calculations when dealing with a discrete random variable, okay? So we're talking about discrete random variables because they are so set, you have to make sure that the equal to or not equal to or that boundary value, whether it's included or not, becomes fairly important, okay? So that's all they're saying there, okay? Analyzing a discrete random variable, describing the shape. So let's talk about describing the shape. So if you look at the APGAR score, okay, and if you were to do a histogram of the APGAR score, it is shown on the bottom of page 364. And if you were to actually describe this, what would you say? Okay, you would say that this is not roughly symmetrical, right? It is skewed to the left with a single peak. Okay, all right, so that's that. Let's actually go to Pete's Jeep tours, okay? So let's have Kat, who has now decided to join us, read the problem on page 365, Pete's Jeep tours. Kat?
Sorry, my internet is not working today. Pete's Jeep Tours offers a popular day trip in a tourist area. There must be at least 2 passengers for the trip to run, and the vehicle will hold up to 6 passengers. Pete charges $150 per passenger. Let C equal the total amount of money that Pete collects on a randomly selected trip. The probability distribution of C is given in the table. Make a histogram of the probability and distribution. Describe its shape.
Okay, thank you. So you have a probability distribution here. So this is the money he's going to collect. This is the revenue, right? And obviously there are costs here. We're not talking about costs here. We're talking about the money, just the money that he's going to make on that trip. So you have to have at least 2 people. Okay, obviously it's $150 per person. Okay, so if you had 2 people, you're going to make $300, and so on and so forth. Okay, since you can have what 2, 4, 6, up to 6 passengers. 6 passenger would be max capacity, right? Okay, so these are the discrete values. So this is a discrete random variable probability distribution, right? Because you have the probabilities underneath there. Do they add to this 1? Let's see, I have 0.4, 0.6. Yes, they do add to 1. So this is a correct probability distribution, right? So if you look at page 365, it shows the histogram, right? I'm not going to go over that. Okay, it's pretty simple, right? And then the graph is roughly symmetric. Look, it's roughly symmetric, all right? A single peak at 600, okay? In other words, 600 is the most likely thing to happen, okay? All right, so that's good. Let's flip the page. Let's talk about measuring the center, okay? So measuring the center. So what would you, if on any given day, how much more, any given trip, right? How much money do you think Pete's gonna make? Okay, well, the probability of this happening is this, the probability of this happening is this, and so on and so forth. So wouldn't you just go ahead and multiply these together, and then add them together? So if you did this, I get what, $45. Add this together, you get what? 112.5 looks like. Add this together, you get 210, and you multiply this together, 1/5 of that, 150, and it would be 45, and then you would just go ahead and add these together, right? And if you do that, what are you going to get? 3562.5. Okay, so it's 562.5. So this would be your expected value or the average, right? Because this is what you expect. On average, this is how much money you expect to make on a trip. Okay, all right, so let's look at the definition on the bottom there. The mean, or the expected value of a discrete random variable, the mean of a discrete random variable is its average value over many, many repetitions of the same chance process. And it shows you that, yeah, the mean mu sub x, the mu sub x is equal to E of x, which is nothing more than the addition of all these together, right? You multiply these 2 together, and then you multiply these 2, you add them all together, and that's all it is. Okay, so we're not going to do the APGAR score one. Let's go ahead and flip the page. The standard deviation, okay, of this same probability distribution, all right, if you go to page 368, there's a green box there, and it shows you how to calculate the standard deviation. The standard deviation is you take, since this was my mean, I would take this guy, and from this subtract this guy, right? So I would subtract the 300, then I would square that, and then times it by the 0.15. Okay, so the next number would be 562.5, or actually 450 subtracted by 562.5. Square that and then multiply it by this. And this guy, 600 minus the 562.5, again, square that and then multiply by 0.35 and so on and so forth, okay? I'm never going to ask you to do this, okay? But you do kind of need to know, logically or fundamentally how this works, because how are you going to do this? How are you actually going to do this? The way you're going to do this is you're going to put this into L1 and L2, right? And do a run of 1 var stat. You're going to do stat, calc, and then do a 1 var stat, and it'll tell you what it is, okay? And that is actually located on page 370. 370 tells you how to do that. On 370, the Technology Center, okay, you would go to stat, calc. This is after you have to go stat edit first to put in the L1 and L2. Once you fill in the L1 and L2, you can do stat calc and do the 1 var stat. Okay. So that's how you would find the variance or the standard. We're just talking about the variance here. It would be the variances. Okay. So that's the variance, and the square root of the variance is the standard deviation. Okay. So there we go. So okay, so we're good there with the green box. Let's go ahead and move on to the continuous random variables. A second before I go any further. Just make sure I'm not supposed to stop here. Okay. Okay, so the continuous random variables. In continuous random variables, let's go to page 371. In page 371, there's a green box that says continuous random variable. A continuous random variable can take any value in an interval on the number line, okay? Whereas a discrete one can take only specific ones, and there are gaps in between them, okay? All right. So let's go and let's look at the bottom of page 371. There are 3 paragraphs there. I want you to go ahead and read that on your own. So if we had a continuous random variable and it runs from 1 through 9, okay, or 0 through 9, it would be exactly like this, right? 0, 9, 5. The height being here is 1/9, and the reason why the height is 1/9 is because the area underneath this curve right here, okay, area underneath this bar, okay, it has to be 1 because when they add together, or the area under the curve has to be 1. Okay, so that's where you get the 1/9 here. Okay, so if you wanted to find what the probability is between 3 to 7, you would go 3 and 7. You go like this, right? So now you have 4 on the base and 1/9 on the height, so it would be 4/9. Right? That would be the probability, right? Okay. So the green box on page 372 that says the probability of an event involving a continuous random variable is the area under the density curve and directly above the values on the horizontal axis that make up the event. Okay, just like we just did right here. Okay. So let's go and see if we can do the example on page 373 where it says young women's heights. Okay, so if you look at the young women's heights, right? Says the heights of young women can be modeled by a normal distribution with a mean of 64 and a standard deviation of 2.7. Suppose we choose a young woman at random and let y be her height. Find the probability that the height is going to be between 68 and 67. So basically I'm going to have mu was 64, standard deviation was 2.7, and I want to know the probability distribution between 68 and 70, right? This is what I want to know the area underneath this curve. Okay? To find the area underneath this curve, we will just use our good old friend norm CDF, right? Where the upper bound, the lower bound would be 68. Upper bound would be 70 with a mu of 64 and a standard deviation of 2.7. And you just go ahead and run it, right? You just go ahead and run that, right? Okay, and the other thing was what we need to, so this is the probability that a randomly selected young woman has a height between 68 and 70. That would be the interpretation, okay? All right, so that's that. And with that, we actually did 6.11 and 6.12 together. So we actually finished 6.1 all together. So we'll stop right there.